Hello and welcome to the logic of it all. In this video, we continue talking about graphs, and in particular, we look at concepts such as path and cycles and whether or not a graph is connected. Let's start with the definition of a path. A path in a graph is a sequence of vertices, v0, v1, vn in this case, where for each two consecutive vertex in the vertices in the sequence, there is an edge going from one to the other. So for example, in this sequence, there must be an edge going from v0 to v1, and then an edge from v1 to v2, and then another one from v2 to v3, all the way up to vn. And if that's the case, we call this a path from v0 to vn. The number of edges that you go through when you're traversing a path is called its length. So we count the number of edges and not the vertices when we are talking about the length of a path. And that's an important thing to remember. And usually we restrict ourselves to simple paths, and a path is called simple if we don't repeat any of the vertices. So we visit everything, we don't visit anything more than once, basically. And here's an example. So we have this undirected graph with 6 vertices, and we want to find 2 paths from A to F. Now the first one, the simpler one, is going from, so when we talk about path, what you should think about is we want to go from A to F. We want to find a way to traverse the graph and go from A to F in this case. And the easiest way to do that is going from A to B and then from B to F. So that's a path, ABF, which goes like this, from A to B, and then from B to F. And we used only 2 edges, which means that the length of this path is 2. Now, there's another way of going from A to F, and that is from A to C, C to D, D to E, and E to F. And that's also a path from E to F. And in this path, from A to C, C to D, D to E, and E to F, we traversed 4 edges, and that means that the length of this path is 4. Now here's another example, and this time our graph is directed. So the first question is the sequence A, C, D, E a path? And if you look at the graph, first going from A to C, you see that there is no edge from A to C. We have an edge going from C to A, but in a directed graph, that's not the same as going from A to C, which means that this sequence is not a valid path because there is no edge from A to C. So if that's the case, then the follow-up question is, can you find a path from A to E? And to go from A to E, you can go from A to B, and then B to D, and D to E, for example. And that's a path with 1, 2, 3 edges, the path of length 3. Another way of doing that is going from, let me change color, going from A to D, and then D to E. That's another path from A to E of length 2, and so on. So you see that it's possible to have multiple paths from one vertex to another. The next definition is the definition of a cycle. And a cycle is very similar to a path, except that it starts and ends at the same vertex. So you start from a vertex, you go and visit some other vertices, and then you end up at the same vertex that you started from, and that's called a cycle. And again, similar to path, we are more interested in simple cycles, and a cycle is called simple if you don't visit any of the vertices in between more than once. Obviously, the first and the last vertices are going to be the same, so that will be repeated, but other than those, no other vertex is allowed to be repeated in a simple cycle. So here's a graph. Again, it's an undirected graph, and the question is whether you can find 2 cycles in this graph. And if you again look at the graph, one cycle is represented by this triangle here between A, B, and C. So you can, for example, say A, B, C, A is a cycle. And the length of this cycle again is 3 because there are three edges, involved, A to B, B to C, and C to A. And then there is another cycle going from A to C, C to D, D to E, E to F, F to B, and then finally B back to A. So here are the two cycles. And you see that except for the first and the last vertices that are the same, nothing is repeated. The same for the second cycle, which means that both of these are simple cycles. Here's an example with a directed graph. So if you look at this graph and we are looking for a cycle, we can go from A to B, then B to C, and C back to A. So that's a cycle, A, B, C, A. And the length of that cycle is 3. Now, the next question is, how about ACBA? Is that also a cycle? And the answer is no, because similarly to path, we already covered this, there is no edge going from A to C, so this is not considered a cycle. Now, the concept of a path is used to define whether or not a graph is connected. And this is an important concept in graphs because if you think of graphs as networks, we want to know whether or not we can go from one point in the network to another, whether they're connected or not. And the definition is simpler for undirected graphs. So we start with undirected graphs. And then for directed graphs, it turns out that there are two different definitions for whether or not a directed graph is connected. So for an undirected graph, we call it connected if for every two vertices that you choose, there is at least one path between them. So in that case, we call the graph connected, And if you can find two vertices with no path between them, then the graph is not connected. For a directed graph, the first definition, which we simply again call connected, is defined as follows. We ignore all the directions on the edges. We pretend that the graph is an undirected graph, and then ask the same question. For every two vertices, there must be at least one path between them. Okay, so this is the definition of a directed graph being connected. As we will see a little bit later, there is a second definition for directed graphs, which is a stronger definition. But for now, let's see an example of this definition for undirected and directed graphs. So here's an example for an undirected graph. So we have two graphs. The question is which one is connected. And for the graph on the left, you can see that the graph on the left, there is no path between, for example, A and D. If you want to start from A and traverse the edges, there is no way that you can get to D, or from D to E or D to C and so on. So for that reason, the graph on the left is not connected. On the other hand, the graph on the right, any two vertices that you choose, like A and D, for example, you can go from A to B and then from B to C and C to D. Or D and E, for example, if these are the two vertices that you choose, from D you can go to C and then to E. So any two vertices that you choose from the graph on the right, there is at least one path between them, which means that the graph on the right is connected. Now, when we get to directed graphs, here's an example for that. So this is a directed graph with 5 vertices. The question is whether or not it's connected. And the definition says, ignore the directions, treat this as an undirected graph. And if that's the case, then it's easy to see that if you remove the directions, then there is a path between every two vertices that we choose. And because of that, this directed graph is considered connected. But this is not a very useful definition for directed graphs because, for example, if you want to go from E to A, there is no path taking us from E to A. So why are we calling this graph connected? Or from E to C or E to B and so on. And because of that, there is a second definition for directed graphs, and this is called strongly connected. So In the strongly connected, we do not ignore the direction of the edges. So we call a directed graph strongly connected if for every two vertices that you choose, there is a path from V to W, and of course from W to V as well. So in this case, now we are respecting the direction of the edges when we talk about the path here. So this is a stronger notion, which means that not every connected graph is going to be strongly connected. Okay, so for example, if you look at this graph with three vertices, it's a directed graph. If we want to only consider whether or not this is connected, which means we ignore the directions, and in that case, it is a directed graph. But if we want to know whether or not it's strongly connected, we ask the question whether there is a path between every two vertices in this graph. And for example, if I choose C to A, you can see that there is no path taking me from C to A or from C to B, which means that this graph is not strongly connected. So connected, but not strongly connected. Now, how about this one? Is this graph strongly connected? So what you need to check, and you can pause the video here and check it yourself, but every pair of vertices that you choose, let's say, for example, we choose D and A, okay? So the question is there a path going from D to A? And there is, from D to C and C to A. Is there a path from A to D? Yes, that's from A to D, which means that this graph is strongly connected. I mean, you have to do this for every possible pair, but I leave that to you. But the answer is positive. This is a strongly connected graph. And final definition here, which we will use in later videos, is the definition of a weighted graph. In many applications, we want to assign some weight or some cost to each edge in the graph. So for example, if you're thinking of the nodes as different cities on a map, and then the edges are the roads connecting these different cities, the length of these rows is not the same. So one of them are some of them are shorter and some of them are longer and so on. So by assigning weights to these edges, you can make your model a more accurate representation of the map. The other thing could be the cost. It could be that some of the edges are more costly to use than others. So as we will see later, weighted graphs are used for modeling these type of situations, where every edge is assigned associated with a number, and for our purposes, usually the number is positive. It doesn't have to be necessarily, but usually we consider the cases where the weights are positive.